Okay, so welcome everybody also from my side to today I want to introduce you to a novel power electronic device, the diode-assisted gate-commutated Thyristor, and this device I call in short the Diode-Assisted. And during my work, I mainly focused on the analysis of its current interruption capability and its feasibility in the medium voltage direct current hybrid circuit breaker application. So the first question arises when we talk about novel devices is, why do we need them? We have a lot of them and they work pretty fine. Right. So yeah. So we have a lot of them and they work pretty fine. So to give you a brief overlook, so my device, its main aim or its main feature is its very high current interruption capability. And this we need for novel power electronic, for protection schemes for interrupting DC fault currents. And this DC fault currents emerge because we have novel grid structures, the MVDC grids, and they need new protection schemes. So when we now look at MVDC grids, so this is the grid structure, how it looks nowadays. It's mainly AC, and we have already some point-to-point high voltage DC connections. But the idea for the future is to not just have this point-to-point connection, but also a meshed HVDC grid, and not just on the high voltage level, but also on the medium voltage and the low voltage level. And during my work, I focused on the medium voltage level. So why do we build this grid? What is the advantage, not just for MVDC, but for DC in general, is that we have a more efficient power transformation and distribution. It's possible. So when we convert the energy in DC, we can use power electronic devices, and they have a better efficiency in transformation. And when we want to distribute the energy for long distances, we also don't have the reactive power, why we are more efficient. So we also can increase the flexibility in the power flow control, basically because we use power electronics converters. So we have a simplified integration of battery systems, renewable energy sources, and fuel cells. And of course, we have a lower resource demand because we can better utilize the cable cross-section because we don't have the reactive power. So when we now look at this grids that looked so advantageous, I brought you a picture how it can look like with all the possible applications. But the problem is that we don't have these grids right now. There's still a lot of research. So therefore, we have a campus MVDC grid to better understand how these grids can operate and also to research how the protection of these grids can be possible. So the campus grid goes from the Ion Research Center, which I think you maybe can see is over there, to this building and to the CW building next to us. So this grid has a voltage level of 2.5 kilovolt, and I use this grid as a main base to develop a protection scheme for this particular voltage level, because MVDC can still mean a lot of things. So when you now compare the faults, what is the difficulty when we want to interrupt fault currents? So when we look at the conventional AC grid or AC current, we have a natural zero crossing. So therefore, there the fault interruption is way more easy because we can interrupt it with a mechanical breaker just when the fault enters its zero state, and therefore, we can just use mechanical breakers. In AC, we have a straight line, no zero crossing, and when the fault occurs, it just rises up, and we need to interrupt very high currents. So there are different fault clearance strategies to how we handle this. One is that the converter have a fault right through strategy. So basically the converter changes its switching pattern to right through a fault. But it doesn't work all the time, and we often also need to really physically interrupt the fault. So therefore we need power electronic based circuit breakers. One idea is to have a solid state circuit breaker that is basically an electric switch, that is in the main conduction part, and there we can interrupt very high currents. The problem with solid state breakers is that they have very high conduction losses, and not ideal to have them all the time in the grid. So therefore, also we have hybrid circuit breakers, which is in research, or also in a few companies that start to develop this already, which is the main topology used for this grid. I will talk about this topology on the next slide. But also what I want to mention is that in DC fault interruption, we have the main problem that the fault current rises very fast. So in AC, we mostly have longer time spans till we can interrupt a fault. Therefore, the fault current is not that high. And in DC, we have a lot of time restriction, and therefore especially need to interrupt high fault currents. So I focused on the hybrid circuit breaker, and that works the following. So during normal operation, the current flows through the mechanical breaker, and when then a fault occurs, the current starts to rise till it gets detected, and then the mechanical breaker starts separating its contacts, and there, while this happens, there's a arc voltage sparking across the device. And then we use the voltage of the arc voltage as a potential difference to a power electronic branch. So simultaneously, the switch is turned on, and due to the voltage difference, then here the fault current starts to commutate. So the electric branch overtakes it, and then we need to wait for some time till the electric strength is restored in the breaker, and then we can interrupt the whole current with the one switch. So here, that's a simulation of fault clearance in our MVDC campus grid. Here it's just 3.5 kiloamps, but depending on which kind of position the fault is or what kind of grid we have, this fault can be way, way higher. So after that, the fault current commutates to the parallel snubber capacitor, which is there to protect the device from over voltages. And then the whole fault current is, the fault energy is dissipated in the parallel Thyristor. So the main requirements for our power electronic switch is that it needs to have a blocking capability of 2.5 kilovolt. And the main feature is that we need a very high current interruption capability. And of course, the voltage of our power electronic path needs to be smaller than the arc voltage to ensure a fault current commutation. So I will structure my presentation the following. I will first want to introduce you to power semiconductor devices, which can be used for the MVDC hybrid circuit breaker. And with this, introduce you to the novel device. Then I will follow up with a prototype design and construction, and talk about my experimental and simulative verification of this prototype, and close up with the feasibility assessment. So when you think about power switches for high power application, you will mostly think of an IGBT, the insulated gate bipolar transistor, which is the standard device for high power application. And it has also a very high current interruption capability. I think there are devices on the market that can interrupt 6 kiloamps, so they could be used for a hybrid circuit breaker. Why is it not done very often? Because these devices are limited to its conduction current. They're not prone to interrupt high surge currents. One reason for this is when you look inside the device package, you see it's not just one massive chip, but you have multiple chips paralleled. And therefore, it's not prone to surge current, and also the device doesn't, its operation function can be destroyed when very high currents flow. And there's a difference to that when we use Thyristor-based devices. So an integrated gate-commutated Thyristor, short IGCT, is a Thyristor-based device. So it can, during conduction mode, it actually behaves as a diode, and then we have one massive chip. And the advantage of this is then that we can apply very high surge currents. So the device can withstand way higher currents for a short time. That is mentioned in the data sheet. The only thing that happens, it overheats. But the limiting factor here is its turn-off capability, because we can just turn off this device by actively withdrawing the whole current out of the gate. So this is the limiting factor. And then here comes the research question: how can we optimize this turn-off behavior to turn off as high a current as possible with one single device? So here I brought you a schematic of an GCT wafer. So how does it operate? So when it is in conduction mode, it is flooded with charge carriers, and we want to turn off the device by withdrawing these charge carriers out of the gate. So the turn off process is as follows. So the gate current, the whole current starts to commutate out of the gate till it reaches the anode current, and simultaneously the cutoff current declines to 0. And this time span is then called commutation time. So it's the time till here junction 3 becomes reverse biased. So this time frame is very critical for our turn-off mechanism, because we want to withdraw the charge carriers as fast as possible and as homogeneous as possible to don't have any hotspots. So the next phase is then that still there is some charge carriers here in the P base. So the gate current is still here a plateau till all the charge carriers are removed, and then junction 2 enters a blocking state. So the voltage rises across the device, and at the same time the anode and gate current diminishes. So this storage time is then also critical. And we want to now say, what is the turn-off capability of the device? We defined a so-called unity gain turn-off criterion that says that the commutation time needs to be smaller than the storage time. In this two-dimensional model, it will always be the case, but in reality, the wafer is three-dimensional. We have multiple of the cells in parallel, so not every cell behaves the same. So when we just measure the device, we can use this two-dimensional criterion to just know if we are in a safe margin. So how is the gate current now forced to commutate out of the gate? In an IGCT, we have a pre-charged capacitor in the gate path. This capacitor is normally charged to -20 volts. And then when we turn on the switch, we have a potential difference from the gate path to the main conduction part. And therefore, according to this equation here, we can define the turn-off mechanism. The drawback of this structure is that we have the capacitors, and the capacitors become very bulky. When we want to, the higher the current is that we want to turn off, the more energy we need to store in the capacitors. So therefore, the driver gets more complex, and we need some time to charge the device, and also our strain inductance becomes higher. So the idea to optimize this is then with a new device, the diode-assisted gate-commutated Thyristor. And here we use diode as the main voltage source in the conduction part. So we have here a forward voltage, and then we have a short between gate and cathode during the turn-off mechanism, and therefore we have a potential difference. Diodes are normally not used as voltage sources. I will talk about this later, but here the diodes then have the advantage that they have the voltage just dependent on its conduction current, and we can design the driver very way easier with a lower strain inductance, and we can have higher voltages here in the for the diodes. So for the theory, let's see how the prototype could have all these features that I just promised. So when I wanted to design my prototype, the first thing I needed to select was the GCT wafer, and there I had not many options because Hitachi is the only manufacturer in Europe, so I had to use Hitachi wafers. And there the problem was that the highest rated wafer had an annular gate structure. So you see here. So the gate contact is in the middle of the wafer. And as I told you, I wanted to decrease the strain inductance as much as possible. That's the whole point of this device. So how can the strain inductance be small? By placing the diodes directly on the wafer here in the middle. And then I needed a contact between the gate and the MOSFET and then to the cathode. So I placed a copper ring around them. So here you see the commutation loop inductance, and that is the smallest way or the most efficient way you can have a small strain inductance. The drawback was I could not contact the outer area, so my wafer was just utilized for 25%, and therefore has scaled down rating to 1.3 kiloamps. And yeah, so all my measurements can be scaled up, but I was just limited to this. At the end of my work, a different wafer occurred on the market with the outer gate ring structure, so that would be the perfect wafer, but yeah, it was developed too late. So when we now look at the other design parameters, so here's the equation for the commutation loop. So I needed a very high voltage for the diodes. Diodes are usually not used as voltage sources. Normally you want to decrease losses, so you need a very low voltage. But when you look here, how the voltage in a diode is created, you have once the threshold voltage. That's the voltage from the PN junction. That's normally 0.7, 0.8 volts. And then you have a resistive part, which is for power diodes also very low, because we have a so-called conductivity modulation that decreases the conductivity, even though we are in very high voltage, very high currents. So I had multiple options. I could stack a lot of diodes in series, but then I still had a higher strain inductance, so not a good idea. So fortunately, I got help from Infineon, and they radiated diodes for me. So how did they radiate them? They radiated them with electrons, and additional electrons here in this layer decrease the diode conductivity. And then because the electrons created new recombination centers, and that decreased the charge carrier mobility. So when I used 3 of these diodes for a forward voltage of 10 kiloamps, there was a forward voltage of 50 volts. So that are diodes that I think will not be used in any other application, but with this, I could use the diodes as a voltage source. So there's another parameter that needed to be optimized. That's the strain inductance. I briefly mentioned that this is the smallest strain inductance possible. And here I contacted then the MOSFETs. So I used 8 of these MOSFETs around the gate to have an even turn off as even as possible, and I contact them with pressure to get rid of all the PCB traces, so my whole driver doesn't actually see the current. So the whole turn off current goes by pressure to the mechanical, to the MOSFET, and then there is a thin copper piece in the middle to get the gate contact. So therefore, I could design the driver very simple. So basically, the whole driver is just a MOSFET with a GFET. So here's a picture of my whole prototype, and the whole thing is like that small. So when you compare it to bulky IGCTs, where you have the huge capacitors and the whole turn-off current has to go through the driver, I could eliminate this with this design. So there also needed to be a mechanical decoupling because the GFETs can't withstand a lot of pressure. So I placed a spring under the GFETs, and yeah, created kind of a flexible PCB by having a very thin copper piece here in the middle. Yeah. So for the prototype design, so let's see how it behaved in an experimental setup. So I could successfully turn off 1.3 kiloamp with this device within the unity gain turn-off criterion. So here you see a measurement of this this highest turn-off. So in yellow you see the gate current, and here mark the commutation time, and here the storage time when the voltage starts to rise. The voltage always looks very small because I had a large snubber, so you don't see the voltage at the end rising up. So you see that there is still a lot of margin between storage and commutation time, so everything is safe. So the device at this point just failed because I have a limited wafer, because I only contacted 25%. But I could use this measurement to characterize my device and build a spice-based simulation out of it. So I could also calculate the strain inductance, and the strain inductance is just 942 picohenry. And this is comparably very small. So for IGCTs, you have some papers that say they have 2 nanohenries, others say say 5 nanohenry. So it varies depending on your driver design, but under 1 nanohenry, I think it's a pretty good small stray inductance. So yeah, I used the simulation to extrapolate my measurements. So here you see the extrapolation where the boundary for the unity gain turn-off criterium is, and with the same wafer, because it depends which kind of wafer you use. The storage time varies. It depends on the doping profile of the wafer. So for this wafer, I used the unity gain turn-off criterium here with this prototype would be 10 kiloamps. And here you see the diode voltage plotted. So you have 50 volts forward voltage at the beginning of the turn-off process, and then the diode voltage changes in proportion to its turn-off current. Yeah. But then still we have the questions, okay, is this now a good turn-off, or we need some kind of reference? So therefore I needed to define what is actually an effective gate current commutation, what's an effective turn-off process. So there are different parameters you can use to define this, and one of course is the speed and the homogeneity of the commutation, because you want to withdraw the charge carriers as fast and as evenly as possible from the wafer. So one indicator for this is the short commutation time. So therefore, I did a lot of measurements with different current levels, and here marked the commutation time. So here you see this black dots plotted in the next slide. And I have a very short commutation time, but what means short? So to compare it to an IGCT, I once took the commutation time and the extrapolated values from my simulation to show you how the commutation for a DAGCT would look like till 10 kiloamps, and then compared it to a simulation of an IGCT. The simulation of the IGCT was very ideal. So I used the exact same stray inductance for the DAGCT, which is in reality would be way higher, but I wanted to compare how the two different turn-off mechanisms were compared to each other, and therefore I wanted to get rid of the factor of the stray inductance. And I used a capacitor voltage of 20 volts, and it also remained constant, so I neglected the internal resistance of the capacitor. So I could see that the commutation time above 5 kiloamps is more advantage or is faster for a DAGCT than an IGCT. And in reality, probably it will be somewhere here, because we have all the nonlinearities in an IGCT, which I didn't consider here. So yeah, we have a pretty short commutation time. There's another indicator that is especially often cited in when the effectiveness of the commutation of an IGCT is looked at. So that's the shape of the gate current. So it's often cited that a high overshoot of the gate current and a current plateau after the overshoot mark an effective gate current commutation. So I wanted to show you that these indicators are also present in an IGCT, in a DAGCT. So therefore, I did measurements, and there I varied the diode voltage. So I used once 3 diodes and other ones just 1 diode, and then replaced the other 2 with a dummy. So I could vary the commutation voltage. And here you see that for a higher voltage as expected, we have a higher overshoot, because we have here, there is plotted 500 amps turn off. And then when the voltage was lower, which is not a less effective commutation, the overshoot is less. And the current plateau is not that visible here, the slope, it goes slowly down. And here for a higher voltage, the whole pulse is more compact. And therefore we know that more charge carriers are removed in the first part. So yeah, so and here you see a bit more measurements of the current commutation with 3 diodes, and here with 1 diode next to each other. So you can see that the indicators are really present there. But when we look at the whole measurements here for 1.3 kiloamps, these indicators diminish. And I told you I want to turn off up to 10 kiloamps. So it looks like the indicators are not very present, and maybe we are worse than in an IGCT. But my theory is different, because when you look at how the gate current commutation looks like here in the simulation from the IGCT, you see it's a straight line, because we have a constant voltage of the minus 20 volts. So therefore, the slope is always the same. And we have here the overshoot, because this overshoot is the reverse recovery of the gate cathode junction. So the higher the slope, of course, then the higher the reverse recovery. And we can use this overshoot as an indicator for an effective gate current commutation. For a DAGCT, this looks different, because the driving voltage is dependent on the current. So the highest slope is here at the beginning. So most charge carriers are here removed in the first third. And then at the end, the slope, of course, diminishes, because the diode doesn't see any current anymore. And therefore, we don't have here this reverse recovery effect. And also then we don't have the current plateau. Therefore, we are less homogeneous in a DAGCT, but still, I would say that we are more effective. So, but how could I prove this theory? By looking at the storage time. So the storage time, as a reminder, is the time that the device needed till a voltage is seen across the device. So we know that when all the charge carriers are removed, the device can build up a voltage. So I did the same measurements as before, once with 3 diodes and one with 1 diode. So as the theory says, that the storage time for 1 diode is way longer, because our gate turn-off pulse is longer. So when I had a higher voltage, the storage time got reduced. So here you see the measurements of the storage time now for 3 diodes for different current levels. The storage time also depends on the turn-off current. Of course, the higher the current, the less effective the gate current commutation. But we can see that it's definitely dependent on these factors. So how could I compare this now to an IGCT? That was challenging, because I didn't have any gate current commutation measurements of the gate current commutation from an IGCT. But fortunately, we had a kind of similar device developed here at our institute, the so-called internally commutated Thyristor. That is basically works like an IGCT. We also have a pre-charged capacitor in the gate commutation path, but in the ICT, this capacitor is integrated directly under the wafer, and we had a very small strain inductance. And the exact same wafer was used as in my prototype, and also just the inner part was contacted. So that was a very good way to compare this both turn-off mechanisms. So I had measurements of the storage time for 1.3 kiloamps. And what is now interesting is that the storage time of the DAGCT was smaller. Here it looks like it's just a little bit smaller, but we have a diode voltage of 15 volts for 1.3 kiloamps. And this diode voltage decreases proportionally to the current. So we would expect, because we have a longer commutation time, that the storage time would also be higher, but it is lower. And here we have to prove that our gate current commutation was more effective. Yeah. So to sum up, here are the 2 main points: that compared to an IGCT, the DAGCT has a higher unity gain turn-off potential, because it has a shorter commutation time for higher turn-off currents, where we want to look like. So we are interested in this kind of area where the turn-off currents are very high. And the other point was that we additionally have a more effective gate current commutation, because of how the driving voltage behaves. So the most charge carriers are removed in the first part of the commutation process. So therefore, we are more effective, and I could prove this by looking at the storage time, and this reduces according to the theory. Okay. So I talked a lot about the advantages, why the DAGCT behaves better. I experienced some failures during my experiments, and I want to talk about them, because there are revealed some effects of the DIGCT that I didn't consider at the beginning, but I could solve them with an adaptation. So the beginning, I had failures before I reached 1.3 kiloamps. And this failure always happened in the tail current phase. So I was safely within my unity gain turn-off margin, and I was safely within my wafer ratings, but a failure always here occurred. And then I started to look more closely at all the different gate currents. So I measured the current across all these devices. And I figured out that there are always two currents that have a negative overshoot. What means negative overshoot? Yeah. 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 So when we have normally we have a gate current that goes here out of the device. When a negative current means that it goes back into the device. So therefore, there are some parts of the wafer that get re-triggered and turned on. So, and then at exactly where the point of this GFET 4 and 5, it was here where the failure occurred. So when you look how my whole setting looked like, so there was a snubber on this one side. And it means that the stray inductance within the whole device was not totally symmetric. And therefore, the failure always happened here at this point because we had oscillations between the GFETs and yeah, this turned on the device. I could get rid of this problem by placing a symmetric snubber across the device. So here you see just multiple snubbers across it. And you can see here, I didn't have these oscillations anymore, and I could turn off the 1.3 kiloamps. But in an IGCT, we have a snubber at one side, and IGCT is also not very symmetric, especially when you look at the driver where the capacitors are on one side, and we don't have this problem. So there, nothing turns on parasitically. So there's the question, what happens here? Why we have a problem that we don't have in an IGCT? And therefore, I had to, we can explain this by looking at the structure. So in an IGCT, we have here this voltage source, the capacitor, which is then stabilizing the gate cathode junction. So even after turn off in the tail current phase, this capacitor is still charged and can therefore prevent turning on the device. So it's not possible that a negative current flows here. In a DIGCT, this diode doesn't have any effect during the tail current phase. There's no current flowing. The device here is blocking. So this junction between gate and cathode is floating, and we can parasitically turn on our device. So the solution is to use an auxiliary capacitor. This adaptation I called DC-GCT, and this auxiliary capacitor has its only function is to stabilize this voltage. So when you look at the turn-off process, the first two phases, the commutation and the stirring and decline phase, works exactly the same as in an DIGCT. So the diode is the main driving force, and this switch here is open. And we just close the switch during the tail current phase and then basically no current is flowing here through this part because the resistance is just way higher than during the main conduction part. But with this additional capacitor, we can stabilize this voltage and prevent any parasitical retriggering. So when you look at the schematic, you would think, okay, it looks kind of very similar to an IGCT or everything that I wanted to avoid. But when you look how the driver looks like, so this here is the auxiliary adaptation. So that's just 300 microfarad capacitors. They're very small. They have a totally different function as in an IGCT. So all the drawbacks I talked about before are still not here in an DC-GCT. Yeah. Yeah, so let's come to the feasibility assessment. So when we compare the device to an IGCT, we have Firstly, of course, the higher unity gain turn-off potential and a more effective gate current commutation, what I already talked a lot about. But we also have advantages when we look at the auxiliary power supply, because we want to have a very reliable device that works good in a circuit breaker application. So why do we have advantages? When you look at the driver for an IGCT, so for a 4.5 kilo amp IGCT, we have a GDU capacitance of 45 millifarad, and therefore an energy stored of almost 11 joules. That's a lot of energy that needs to be charged in the capacitor, and so it needs a lot of time to recharge. And also after every switching cycle, this capacitance needs to be recharged. So there are different demands for a power supply. So the DC GCT has just a few millijoules power demand. Otherwise the driver doesn't have any like power requirements, because we just have simple MOSFET switches. So I constructed an auxiliary power supply to just show how the advantages is and how easy it is to construct a device, a power supply for this device. So the whole power supply we were able to construct under 350 euros, and it had a black start capability. So the advantage is when we have a power supply that's directly powered from the 2.5 kilovolt range is that we have advantages in the reliability. So the topology I used is a two-stage converter. So once a buck converter, then in series with a flyback converter. And here you see a picture of the power supply. Yeah, and it was just, we could just have this high voltage level from 2.5 kilovolt to 20 volts in such an easy way, because we basically have no power demand for the GDU, and can also therefore use a high output capacitance of this driver to ensure that during a fault, which is actually the whole thing designed for, yeah, we can still safely supply our device. And then we have here 2 ports, because we want to ensure that yeah, the device is supplied no matter on which side the fault occurred. So this is one advantage. And then also we have advantages regarding the turn-off capability of the device, because it's independent from external factors such as temperature, aging, GDU charging status, and time restrictions. Because in an IGCT, we are always depending on how the capacitor is charged. Also, its turn-off capability is then dependent on external factors as temperature and aging, and we could all get rid of this by using diodes as the main voltage source, which are just dependent on the current. So, and also we have therefore a low correlation between reliability and cost, because of course we can get rid of all these factors in an IGCT, but then we decrease the cost because we we use a larger capacitor bank, or we use a more advanced power supply. And therefore also we have then advantages regarding the costs, because in the IGCT we have a lower GDU and power supply. Of course, we also have disadvantages, and one is of course the high forward voltage of the diodes. And there we have a critical part when we want to look at the hybrid circuit breaker, because we need a commutation from the mechanical to the electrical branch. So I did simulations of this. So the commutation still works in a fine range. So I would say we don't need any auxiliary adaptions to have this commutation, but of course it would be easier as in an IGCT. And this very high forward voltage, of course, it generates thermal stress, and the losses are not of importance for a hybrid circuit breaker, but it still limits the conduction time. And we have a limited application to the hybrid circuit breaker, because I constructed a device with immensely high losses in its conduction state, so you can't really apply it in other ways than in a hybrid circuit breaker. Okay, so what needs still to be done? I talked a lot about these 2 advantages of the higher unity gain turnoff and the effective gate current commutation. but I could not test this higher than 1.3 kiloamps because I was limited to the wafer I had. So this should definitely be tested with a different wafer and different exhaled prototype. And this commutation from the mechanical to the electric branch, I verified with a simulation, but you should also verify it in a real hybrid circuit breaker setup with a real mechanical breaker to really see how the arc voltage behaves. Okay, then thank you very much.